When I begin this portion of a probability lesson where I'm focusing on the multiplication counting principle, I usually have students take a multiple choice test. In this case, 15 questions. And each of the questions have 5 options, A, B, C, D, E. The sneaky part is what I do is I say, okay, question number 1. But I don't actually give a question. I go question number 1, question number 2, question number 3, and then immediately they kind of get the idea, literally we are guessing. And that's why I call it out the probability all guess exam. So maybe they decide it'll be A, B, C, D, E, and then they want to say, oh, well, we know all the answers usually are C, so we better have a stretch of C's here. And then maybe they just want to start spelling words, and they spell B, E, A, D for bead, and then what the heck, they just like E at the end. So maybe it's bead with the silent E. Who knows? It's just 15 random choices. And then usually the joke is that I'll say, kind of feels like some of my regular tests. And unfortunately, a few students will nod their heads and agree with that. Hopefully that wasn't you. But what I'm trying to emphasize is we're going to use that problem as a basis for future problems in what's called the multiplication counting principle. And that's all it is where you take the number of ways something event A can occur and multiply by events of number of ways that event B can occur. So let's just take a look at something that we've already talked about, actually 2 different examples. One of the examples is rolling a 6-sided die twice. And you could say I'm going to roll a black die, all right? Die. There we go. Times. And over here would be second die. Usually it's in a white die. I'll just put it in green. Okay, that will be called a white die. And there were 6 ways to roll the first die. There were 6 ways to roll the second die. And that kind of goes back and justifies how I came up with 36 different dice rolls. 1, 1, 1, 2, 1, 3, and 2, 1, 2, 2, 2, 3, where the 2, 1 and the 1, 2 were different. All right? Same thing with the deck of cards. If I'm looking at a deck of cards and I'm looking at the face values, and there's the ace, the 2, the 3, the 4, 5, 6, 7, 8, 9, 10, jack, queen, king, there are 13 choices there. Let's put that in a different color, 13, and multiply this by now the suits, and there are both the red suits, diamonds, and hearts. There's the black suits, the clubs, and the spades. There's 4 of those. And if you multiply those together, you come up with 52 cards, what I said would be our standard deck of cards. So why not apply this to other problems? And so one of my classic things is sometimes we go out to a place where they have this fixed meal, and then they give you different options in one list for appetizer. So we have soup, salad, we'll say fries, or we'll say mozzarella sticks, mozz. All right? So there's your 4 options. Then we have our entree, and maybe you're going to get yourself a hamburger. Maybe you're going to get a chicken something. Maybe you're going to do, let's say, steak. You're going all out and doing the steak. Maybe you decide you want to do, let's see here, pizza. Or maybe you're just going to do some kind of pasta. And why did I choose 5? Because here I have 4 appetizers, 5 entrees. And so if I was trying to figure out all the ways I could just order those 2 things, I would have to go soup, hamburger, soup, chicken, soup, steak, soup, pizza, soup, pasta. And there's 5 choices. Then I'd go salad, hamburger, salad, chicken, salad, steak, salad, pizza, salad, pasta. Now we're up to 10 choices. Fries, hamburger, fries, chicken, fries, steak, fries, pizza, fries, pasta. There's another 5 more, 15. And then mozzarella sticks for hamburgers, mozzarella with chicken, mozzarella with steak, mozzarella with pizza, and mozzarella sticks with pasta. 5 more giving me 20 options. Or I could have just said, here's my appetizers, so I'll abbreviate with app, and I could have just said, there's 4 of those, and simply multiply it by my entrees, which is 5. And the reason why I think this would be smarter is I'm still not done, because I technically could have had 8 sides. Maybe my sides are green beans. Maybe my sides are mashed potatoes. Maybe my sides are corn. Maybe my sides are baked beans. Who knows what they are? I have 8 options. So now I would have had to go soup, hamburger, green beans. Soup, hamburger, baked beans, soup, hamburger, corn. And then I still have to do the desserts. All right? And each of those would then have 3 different options because it could be, let's say, a cookie, it could be a slice of pie, or a scoop of ice cream. Well, instead of having to write all those possibilities out, I could have just gone 4 times 5 times 8 times 3 and come up with 480 different possible meals for this particular fixed priced meal special. Okay. Let's continue on because I'm going to continue doing the multiplication counting principle, but I have to know a couple things, especially for, let's say, this situation right here about the die, because when I roll 2 dice, I'm assuming that I can re-roll a 6 on both dice. I can roll a 6 and a 6. If that's the case, then I am dealing with replacement. That would be dice rolls, spinners, true and false questions, multiple choice questions, things that I can reuse the same outcome over and over again. Other situations might be without replacement, as if once I use it, I can't reuse it, all right? Now, if you do matching questions the way matching are, then once you choose a choice from a match, you should not be able to choose it again. If you say that I have, if you're saying it's a matching test and it's going to allow you to reuse the answers, it's just a glorified multiple choice. If you're going to put things in order, let's have students line up at the door. A student cannot be both at the front of the line and the back of the line unless literally the line is one person. If there's more than one person in the line, they're in one spot, not the other. So you can't use them. That would be a situation without replacement. And so where I'm going back to this is how many ways could I have answered my probability all guess exam, meaning this test up here at the top. And so what I need to realize is how many ways I could have answered. Well, this one had 5 choices, 5 options, 5, multiple guesses. This one had 5. This one had 5. And so if I was actually figuring out how many ways could I have answered this test purely by random happenstance, it would have been 5 times 5 times 5 times 5 times 5, and that would have just been the first row, times another 5, 5, 5, 5, 5, followed by another 5 times 5 times 5 times 5 times 5. The reason I'm bringing this up is, wouldn't it have been a lot easier if I would have just simply said, I am multiplying 5 by itself 15 times? Because this is a with replacement. I could have answered the whole test C, all the way down the line. And if you do work that out, it works out to be approximately 3.051 times 10 to the 10th number of ways of doing it. That is quite a large number of ways of randomly guessing this test. And if you really want to see what that digit is, it works out to be, I did work it out later on, to be 30,517,578,125 different ways of doing this. Now, this is where I have a little bit of fun with my students. So let me go to my calculator here. Let's clear this out. And I say, okay, let's just do this for a moment. Let's take 5 to the 15th. And there we go. And let's just say that let's say that you were playing this game and you were going to win. And you could play this literally every day. So how many years would it take if I was to, say there were 365.25 days, and you're literally going to write out all the possibilities? Well, at that rate, it's going to take you 83,552,575 years if you play once per day. So how about we now divide that in 24 hours? Maybe you're going to play every hour, do one of these tests every 24 hours, so that literally you do every single possibility. Well, then it should just take you now 3,481,357 years, because you're going to get to do 24 in one day. So then I say, well, what happens if I want to play every minute? So now let's see, if I do every minute, now it should only take you 58,022 years because now you're playing once per minute. And you can kind of see that this is a very ridiculous number to try to just randomly guess correctly. And so I'm not usually too concerned that students will just get all 15 questions right purely by random happenstance. In fact, the probability of being successful is the probability of getting all 15 right. And as far as I know, the only way that you can do that, and this is where it gets a little interesting, so I'm going to show this out, is that the only way you can get the first question right is getting the one choice, and then the second choice is one, and the third choice is one, the fourth, and the fifth, because literally I have to have the one answer that's correct, and then I'm going to keep doing this, 15 times. So this kind of becomes ridiculous because I could be writing this as 1 to the 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then technically that would be over 5 times 5 times 5 times. See, very, very, very annoying because my handwriting is just getting terrible. And I think I would have just made it easier and say 1 to the 15th over 5 to the 15th. And some students might even have gone and say, well, why don't we just say 1/5 raised to the 15th? Because each chance of being successful was 1/5, and I would need to do this 15 times in a row, and I would totally agree with you. So again, we're saying literally you have a 1 in 30,517,578,125 chance of doing this. Well, let's go take a look at a new situation, but this time we're going to play, let's guess the cards, meaning I'm going to choose 13 cards from one suit. In this particular case, I'm going to choose 13 spades, ace through king, and I'm shuffling them up, okay, and I'm shuffling them up and I'm shuffling them up, and I'm going to show you one card at a time. And so if you're trying to figure out what I'm trying to say is, maybe I'm going to guess that maybe the 6 comes up first. Well, here's the thing. Once I know that the 6 of spades comes up, all right, how about if I put this actually in black? So that at least makes more sense. If I put the 6 up, I can't use it again. This is a case where with replacement, nope, doesn't work like that. This is a without replacement type of situation. Because then the next time I may choose a 9, and the next time after that I might choose a queen, and then maybe I'll pick the king, and then I'll pick a 2, and over here I'll pick a 4, and then I'll pick an 8, and then I'll pick a 3, and I'm not able to use these cards twice. Once an ace gets picked, I cannot expect it to be showing up somewhere else. So then 7, and then 10, and then I have a jack, and what's left? Oh, a 5 right here. There's the 5. Okay, so that's what I've done. Well, one of the things I want you to understand when it comes to without replacement is you have to ask yourself is, do I win because order matters or does order not matter? Well, if I have 13 cards and I ask you to tell me how the 13 are drawn, and everybody's playing this game, and I say order doesn't matter, everybody should win because the 6 is going to show up somewhere, and the 9 is going to show up somewhere, and the 5 should show up somewhere. So it kind of defeats the purpose. I mean, I want to make this a tough competition. So yeah, order does matter, okay? Because if you go, and let's just keep it simple, a 6 followed by a 9 followed by a queen is not the same as if I would have gone 9, 6, queen. I could have had 3 through 13 right, but if I had 6 and 9 wrong, I have not actually gotten a perfection on this particular extra speculative probability mid-lesson. So, how many ways could I have answered the ESPM? Well, let's just think about how many ways I could have answered the first question, the first card. So here's the first card. Well, I had all 13 options. Okay. And if I do the second card, I could have had 12 options. And I could keep doing this down the line. I could keep going times 11, times 10, times 9, times 8, times 7, times 6, times 5, times 4, times 3, times 2. And when I got to the last card, there was only one option left at that point. Well, this works out to be, in this situation, 6,227,020,800, meaning it was actually a better chance that I could have done this than if I could have actually answered this, because there were 30 billion possibilities. This one only had 6 billion possibilities. And if I was trying to be perfect, the probability of perfection, helps if I spell perfection right, how about if I just say perfect, is there is only one way that I could have literally had all those work out. It could have been 1 times 1 times 1 times 1 times 1. I'm not going to write all that out, but I am going to write it out as over 1 over 6,227,020,800. Now here's the neat thing. There is a shorter way of writing out 13 times 12 times 11 down to 1. There is a quicker way than working that all out that way. And for that, you need to learn what is called, ta-da, the factorial. N factorial. No, it does look like an exclamation mark, but it is not. It is a factorial. And what you're going to do is realize that if I see n factorial, I am saying, for this problem, this would have been 13 factorial because it starts off at 13. Then I go 13 minus 1, which is 12. Then I go times 13 minus 2, which is 11. And I keep going all the way down until I get to 1. And I stop. And that will produce the same answer as 6,227,020,800. So I guess what I could say is this is simply 1 over 13 factorial. And because this is a very popular situation, we actually have a key for that on the calculator. So let's just work it out the long way and show you just even with doing this with the calculator. And I'm just going to do this. And I'm doing it hopefully a little faster. And I hit enter. Now I'm going to show you that I could have just gone 13. I could hit the math key, which is right there, move over to the probability menu, which is right there, and lo and behold, there is the factorial. That is number 4, and I hit enter, and I get the same exact result. So yes, you want to learn factorials. But you better understand a few rules about factorials. Okay? Factorials are used without replacements. When you have problems that are without replacement, use factorials, because once you pull a student and put him in front of the line, that student should not be able to be anywhere else. So then you'll have one less student from the choices, and then you'll have one less student after that. So if we were trying to say, write a 26-letter word that used up every letter in the alphabet, it would be 26 factorial, because once I pick V as the first letter, I can't use V anywhere else down the road. Another thing that you should know is that they are not distributive. Let me explain this very simply. Let's just say you want to do 3 plus 2 quantity factorial. Well, that's simply 5 factorial, which is 5 times 4 times 3 times 2 times 1. And if you do this long enough, you do learn some of the first factorials, which is 120. Well, this is not distributive, because if you actually had gone 3 factorial plus 2 factorial, you would be going 3 times 2 times 1, and then you'd be adding 2 times 1. Well, that happens to be 6, that happens to be 2, and that would work out to be, in this particular case, 8. And that wouldn't make any sense whatsoever in this problem. So what I'm saying is, don't assume this equaled that, because it doesn't. And so don't do that. Let's go apply factorials to our problems. I have 6 books to be placed on the shelf. How many different arrangements of the books on the shelves are there? Well, instead of drawing blanks, let me draw some books. Book spot number 1, book spot number 2, book spot number 3, there's 4, there's 5, there's 6. probably don't have gap between them, but you get the general gist. And so literally I can go 6 times 5 times 4 times 3 times 2 times 1, and I come up with 6 factorial, which I told you, well, I didn't tell you, that was 5 factorial, but that would be literally 5 factorial times 6, and so 120 times 6 would be 720. And that's actually one of the little tricks I'm going to show you as we continue on. Let's continue with another example. There are 8 finalists in the spelling bee. The order of the contestants will be determined by a random draw. How many different orders are possible for the final spelling bee? So this is, again, is just lining people in order, because once I pick who's going to go first, they're not going to go a different way. So in this particular case, my first person is going to be 8 possibilities, and then I'm going to go times 7 possibilities, because that's all that's left, and then I'm going to go times 6 possibilities, and then I'm going to go 5 possibilities. I'm going to multiply that by 4 possibilities, then I'm going to multiply that by 3 possibilities, I'm going to multiply that by 2 possibilities, and then there's going to be 1 person left over that hasn't been called, and even though I'm going to multiply by 1, it's not really going to change the number. And this should give you a better understanding of why it would have been so much easier if we just simply said 8 factorial on the calculator. And so let's go ahead and do this problem on the calculator in the prior problem. So let's do the 6 factorial, 6 math over to probability, and go choose number 4, 720, and then we go 8 factorial, and we come up with 40,320. And now that I've come to the end of this page and I've done my examples with factorials, I'm going to call it quits for right now, because the next part of our lesson is going to get into permutations and combinations. And for that, you first need to make sure that you are comfortable when you have a situation that is with versus without replacement, because permutations and combinations are going to only be one of those 2 specific types. In all these problems, I'm applying the multiplication counting principle, even when I'm having things repeat, like my test where I could do multiple choices, A, or when I had a deck of cards and I could only play 1 card at a time, and once that card was used, it could not be used again, or maybe putting the books in order. And when I did that without replacement, there's a good possibility that maybe a factorial could be applied here.